Okay, hello everyone. Finally, let's talk about the multi-cycle architecture. There are several weaknesses to the single cycle architecture that we had introduced earlier. First, it has separate memory for instructions and data. That means that you always have to have two different two different hardware memories for these things. And instead of having two different memories for everything, you'd rather just have one so that peripherals are not quite so expensive because you also have to interface with both of these when you're using the Harvard architecture. This is the Harvard architecture. The instruction memory is separate from the data memory. Clock period for this one also has to be long enough to support the slowest instruction. Now, this is the major problem for the single cycle weakness. Um, the slowest instruction for single cycle architecture is actually the load register operation. Why? Because, well, it has to go through both the instruction memory and the data memory, and then it also has to wait for the stuff to come out of the data memory, um, after which it goes into the register file. Most other instructions, they only either use the ALU and then write that back to the register file, or for read data, it goes through the ALU and it uses the address that it calculated, and then it writes the data, and then however long it takes for the memory to write that, it doesn't really care anymore, unless you need to run another instruction for writing to memory and um, a store register rather. Um, then you have a problem with that. But otherwise, you don't really have a problem with it. The major problematic guy is the load register guy. Now, this is why we have a motivation to try to make the multi-cycle computer. So by introducing multiple shorter steps in the calculation process associated with executing an instruction, we can one, reuse the ALU for PC plus 4. We can use one memory to get both the instruction and data. Just a disclaimer, we didn't do this either. And also, we can use less cycles for easier instructions. Again, Mr. or Miss, LDR is going to take a lot more cycles than everyone else. So just give them more instructions. Um, and the major thing is another major thing that we're going to see is that we can reuse the ALU for doing PC plus 4 whenever we're not using the ALU for doing data processing instructions. The multi-cycle state machine. For the state machine, the thing that happens is that it gets new intermediate states. Remember, initially we go from one architectural state to the other. Whenever we read a new instruction and then we get like a new instruction, the architectural state changes again. Now, what happens with multi-cycle computers is your architectural state goes into a little bit of a detour before you switch to some major states where you can actually read another instruction. So the instructions cause your architecture to go on some sort of detour before it goes back and it can read some sort of new instruction again. And that's basically that's basically the difference of what happened for our state machine now. So what happens is that state variables, or state elements, will now also exist inside the controller to keep track of which cycle we're in. The recommended way of doing this is using one hot encoding, and you can think of it of how to implement a controller yourself after we're done with this lecture. I would recommend use one hot encoding for it. So okay, just as how we started with the single cycle computer, let's build our computer by first listing down or showing the different state elements that we have. Still the same data memory as we used before. Still the same register file as we used before. Okay, so first, we fetch the instruction. As before as well, we're going to try to um, go through the building process of the processor by starting with the load register instruction. So first, we fetch the instruction from memory. PC goes into the data memory, and the instruction comes out. It goes into a register to remember the instruction, and that's going to be remembering the instruction for the rest of the time to follow. For the instruction fetch stage, we want to write into that register so it has an enable. We don't want to write into it when we're in a different stage of the instruction because we don't want the instruction to change while we're executing the instruction. Next, we need to read the register file. So we put 1916 here, which is the register containing the base, um, or rather, I mean, that's also still called RN in the instruction decoding, which goes into a register. That thing is always enabled. And we also take the offset. We put that into the extend stage, and then we get the extended immediate. And then what we do with the base and offset, well, of course, we add them. So we use the ALU for that. And we say we tell the ALU plus. Also, in the previous section, I should have said, we tell the im source that we're doing a memory instruction, and the ALU result goes into a register as well, which is also always enabled. And let's call that the ALUOut register. Now that we have the ALUOut over there, in the next stage, we can pass the ALUOut all the way back to the address, and then we can use the address, which was the base plus offset that we calculated, to access the data memory again. Oh, so I'm sorry, we do have the shared instruction in data memory now. I actually forgot about that. So anyway, we put in the address and we access the data from this memory, and it comes out over here, and then we pass the read data not into the instruction because it's not an instruction, but we pass it into a register that has data in it. And this thing is also always enabled. So I mean, you can see that this thing contains instruction most of the time, unless you're going to use data in the cycle immediately after, in which case you put read data and then you have to read it, or else it's going to be overwritten by some random thing that's been being read from the memory. So use it immediately after. But using it immediately after it's fed from data, we put it through a multiplexer now. So we introduce this multiplexer right here so that we can choose between this and this. Also, why is my pen black? Okay. So now we introduce this multiplexer so we can choose between this and the result of the ALU. And then we write that back into the register file, and that basically completes the LDR at the data path that load register needs. But there's something that we're forgetting. We need to increase PC. And one of the main motivations is actually to reuse the ALU. So reuse the ALU we shall. We introduce a multiplexer over here that chooses source A of the ALU. If we choose 1, then it chooses PC, it goes up here, and then we introduce another multiplexer over here that chooses the immediate 4. So PC, ALU control is plus, we get PC plus 4 from the ALU result. And then we introduce yet another thing here so that PC plus 4 can immediately go out instead of having to go through this extra cycle process. So it comes out of here and then goes back into the PC, and then whenever we want to write PC, or um, whenever we want to whenever we're in the stage where we want to write PC, we assert this PC write. Okay. So that's basically it for everything that the load register needs. So let's look at what store would need. The only thing that store needs, apart from the thing that we had before, is that store actually uses the destination register as an input to the register file. So you can see this is also 1512. So you can have this thing fed into here, and then this thing will now contain the data register. So RD is the data register for stores, and now this thing is fed into the write data of the data memory. This thing also still remembers it's always enabled, so you have to write into the data memory after you read into the register file. Okay. So, okay, but that's basically all the store instruction needs. For add with immediate addressing, we don't really need to add anything else to the data path. So you have, okay, the thing, the destiny, well, RN is here, immediate addressing. So the immediate is fed here. We just have to say 00 over here for the immediate source. And the destination register is still here as well. So we don't really need to change anything about the data path. But for data processing instructions with register addressing, we need to choose RA2. Remember that earlier we were forcing 15 to 12 over into RA2. Now we need to choose between RM, so RM or RD. And now this is the RM or RD multiplexer. We can choose between that. So if we have a data processing instruction that was register addressing, then we just pass it through here and choose 0. And then that would be stored in this register the very next cycle. We also introduce this extend, rather, instead of introducing a multiplexer, we extend this multiplexer. So now we can choose between the extended immediate for or RM. So then if we choose RM, we can have RM plus RN over here if we so choose RN. So that's basically the reason for that multiplexer. Okay, but that concludes it for the data processing instructions. Now we have branch instructions. Branch instructions, on the other hand, they have the thing that they need is an immediate of 15. So they want to access 15, which gives us PC plus 8 over on this side. So we want to get PC plus 8 over in this on this side by feeding in 15 to RA1 for branch instructions. So that's what this multiplexer is for. So we choose one something for just to get 15 on this spot. But that's basically all a branch will need to add to the instruction. And with that, actually, we can cover all the instructions that we used to be able to cover for the single cycle data path. And now, what we have is just a more complicated data path than we had before. So the thing is, how do we use this? Because we have multiple cycles. So we have multiple control signals for the multiple sets of control signals for a specific instruction, because now a specific instruction has like 4 cycles. You have to generate different control signals for those 4 cycles to choose like specific things for this multiplexer or some other multiplexer. So how do we do that? Well, refer to this instruction manual. Instruction manual. Write enable signals are 0 unless otherwise specified. Okay, this is more a manual on how to listen to the following part of the lecture. All other signals are X unless otherwise specified. The first step is always fetch the instruction and PC plus 4. So, okay, in the first cycle of any instruction, you fetch the instruction and you do PC plus 4. The second step is always to decode the instruction for any instruction, and you do calculate PC plus 4 plus 4. Why do we calculate PC plus 4 plus 4? Remember, we had 2 adders in the single cycle processor. One that was calculating PC plus 4 and one that was calculating PC plus 8 from PC plus 4. So now the second step is to reuse the ALU again to calculate PC plus 8 to write it into register 15. So, okay. And also, here are the instructions supported by this data path. We can actually support, we don't actually, okay, we don't support B because the memories here do not support writing B into stuff, and the register file that we have does not really support writing only the first part of only a specific byte as well, because we don't have masks, nor do we have a part that puts 0 on some parts of the thing. But okay, LDR and STR, no byte load stores, and we only have immediate addressing. I'm not gonna explain why we can't do register addressing, but I will point out that store is the reason why we can't do register addressing. So you can try to find why. It's going to have some sort of paradox if you try to do stores with that. Okay, we can do add, sub, and then or with all of its addressing types. Branch, um, yeah, branch, and we cannot write to R15 because this thing has specific specific control control considerations that we don't actually consider at the moment. So okay, I'm going to discuss first how do we do the first cycle for everything. Okay, the first cycle for everything is to fetch the instruction. The PC comes out of here, it goes into address. So this thing is 0. Now from address, the instruction comes out and goes into this register, which we want to write into. So we turn this into 1. But other than that, what do we want to do? We also want to calculate PC plus 4, as I said earlier. So now we're going to route the PC all the way to here. So we choose 1 here. We tell the ALU to add, and what do we add? We add 4. So ALU source B is 10. Then we get an ALU result, and then we route that down here. So we choose 1, 0 over here. And then that goes all the way back to PC, which we tell it to write to itself. We say, okay, PC, write to yourself, PC plus 4. So, as I said earlier, all the writes, anything unspecified here, the writes, and the other sources are um, either 0 or X. So 0 if it's a write, and if it's not a write enable, it's going to be X. So, that's that. Okay, instruction 2 for everyone. Decode. So now you have the instruction over here. So we're going to have the instruction over here, and we're going to pass it to the control so that the control can see what the instruction is and determine the control signals accordingly. Now, the thing that is special about the decode step is for reg source, you have two unknown here. And this is actually something that's going to make your state machine a mealy state machine. Or if you want to make it more, then you have to have a separate combinational block for the decode step. But anyway, the first one of this that is fed into here. So this is 1 if branch, 0 otherwise. So 1 if B is 0. Now this part is instruction specific. So this thing is instruction specific. So if you have an instruction that needs to use RM, then it would be 0. If you have an instruction, say read, then it would store register rather STR. If your instruction is STR on the other hand, then you will have to put 1 over on here. So it is dependent on the instruction. But okay, this part is basically the part of the decode step that is going to be relevant. But anyway, after all of that decoding, you're going to be passing two different things over onto here, which is going to be the main product um, of your decode step. But forgot to put here. We also need to calculate PC plus 8 over on the cycle 2 decode step. So we're going to pass this over here, then here. So ALU source A has to be 1. Then it's going to be here. And we choose 4 again. So that's 1, 0. And ALU control is plus. And ALU result comes out. Then we choose 1 0 over here. Then that travels all the way down here. And it goes into R15. Now, R15 isn't connected to RegWrite, so we don't need to make RegWrite make RegWrite 1 here. So R15 just automatically accepts the thing whenever it wants to. So I would say there's a separate control signal for it. Depends on the implementation inside the register file. But okay, as said before, all other writes for this one is all other writes are 1 for no for this. Okay, all other writes are 0. I mean, all other writes are 0. All unspecified non-write control signals are X. Okay. So what's the aftermath of decode? Well, after decode, you're going to have over here. So if it's branch, so the top part of this thing will contain if it's a branch, it will contain the contents of R15, which is PC plus 8. Else, it's going to contain the contents of Rn. This bottom part is it can either be the contents of Rm, it can be the contents of Rd, or you don't care. So okay, when is it RM for register addressing data processing instructions? When is it RD for store? When is it don't care for load and branch? Or for immediates, like for immediate addressing data processing instructions. But basically, that's the aftermath of decode. That's what you get from the different possibilities that can happen in the decode step. So okay, let's talk about next. Let's talk about the third cycle for store and load operations because they have the same third cycle, which is called MemAdr. So for this step of the store and load cycle, you have here 1512 being fed into RA2. This in case it's a store. You still also feed RD. So you're feeding RD over into here in cycle 3 for store. And then in case it's a store, by the way, so load doesn't really care if you feed that into it. Um, but basically this means that registers needs to be 1 for this specific control structure if we're going to have the same state for store and load in cycle 3. So the offset is going to traverse through the extended immediate, and we're going to choose 0, 1. Since we're going to add the offset, allo control is plus. But the thing with this is this thing will already be outputting the base from the Rn that we put into it from the earlier decode step. So Rn, which was mentioned in the last slide, now contains the base for this instruction, and it goes into this register over here that will contain the target address. Now, after that, so next cycle for store instructions. Now we have here RD. It's going to be outputting the right data, so that's going to be fed into the memory over here. Sorry, not write back to RF, just write back in general. And then this thing now containing the address goes into 0, 0. So it goes through 1, and then now it's being fed into the address. And then MemRead is 1 because we want MemWrite to be 1. All other writes are 0, everything else is X. Okay. So that's cycle 4 for store, and basically after this cycle, store is done. What's cycle for load? Well, cycle for load, okay, we still have the address over here, so we're going to pass that 00, and it's going to be fed into the address of the memory. So this is 1. We don't want to write anything into the memory, so that's 0. Uh, this you don't really care about this because we're not writing into the memory. But basically, since we have the address feeding, we have data coming out of the memory, and we route that down here. So we don't want to write that over onto IR, right? So that's 0 as well. And it's being fed into this register, and that's basically cycle 4 from the memory. Basically, you go from ALUOut into the memory, and then you pass that data over onto this register. Next, in cycle 5, you take the data from this register, it comes out over this end, and then it gets fed back into this multiplexer again, which we need to choose 0, 1, 4, and then it goes up into the register file. So right back to RF this time. Okay, this is where right back to RF comes from. And we set regwrite to 1. The destination also needs to be fed here, but since we haven't written into anything into instruction, remember IR write has been 0 all this time, so the same instruction has been being fed out of it, so RN is still coming into here, thus RN is RD pala rather, RD is still correct. So okay, that's basically it for the things that we need for LDR cycle 5. Okay, data processing. Cycle 3 for data processing is different from store and load. So what you have for this one naman is you have two different types of cycle 3 for the data processing instructions. One if it's a register addressing instruction, and one if it's a immediate addressing instruction. So if it was a register addressing instruction, this thing contains RM, and this thing up here contains RN. So then you want to route this through here. So we put that 0. We say we don't know. It depends on the data processing instruction. And then we have RM being fed over here. So we put 0, 0 over here. And again, we don't know the instruction for the ALU because it depends on the specific instruction. But we feed that into this register. Okay. Now for cycle 3 for immediate addressing, we're going to have here from the instruction being fed into the immediate extender. Goes into here, so we choose 0, 1 for this guy, and then allo control still don't know. This thing contains RN, so we route 0 over here. So now we have RN done with some sort of operation with the immediate, and then we put the result over onto this register, and that's basically how that happens. Okay, now cycle 4 for data processing instructions. All the same. What you have here in ALUOut, you pass through this multiplexer, which is fed into this data path, and then travels all the way back to the register file, where you have a 1 for the reg right now, and then A3 still the destination register because this instruction never changed. We never asserted IR write at any point in time after we first decoded the instruction or after we first fetched the instruction. So that's still going to be being fed into that. And that's basically all the control signals needed for data processing cycle 4. For branches, branch cycle 3. Okay. For cycle 3 of branch, what do you do in branch? You replace the PC. So after the decode step, what we have for branch is we fed register 15 over here, right? So after the decode step aftermath, this thing now contains PC plus 8. So we route PC plus 8 over here. We get 0. And then you add again, and you get the immediate from the instruction that has not changed. I repeat, it has not changed ever since we fetched it. And we extend the 24-bit immediate of the thing, and then we add it to PC plus 8. So this thing we need to choose 0, 1, and now you have label minus PC plus 8 plus PC plus 8 equals label. So now you have label coming out of here. So this is label, and then it goes out, and then you put it back into the PC, and PC write is 1 for uh, PC write is 1 for this. Or actually, okay, I would say you don't know if PC write, actually for all of these you don't know what the ending write is. Okay, but the writes are assuming is true. If the condition is not true, meaning you shouldn't finish the instruction, then the writes are all false for everything. Like, write is false every time if condition is not true. And also, if condition is not true, you can just, you evaluate the condition in the decode step. So we didn't take that into account, but I would say we add that to the control, if ever, that if condition is not true, then just, cancel operation. Just fetch the next instruction, um, because there's nothing to do. The condition is false, so the instruction doesn't have to be performed. So anyway, result source for this one is 1, 0. Has to be. Maybe I've forgotten one of those. Okay, never mind. It doesn't seem like I forgot any multiplexers like this one. I hope. But anyway, if you pass through a if we pass any signal through a multiplexer, it has to choose that specific signal. Okay, that should be like that should be straightforward naman. If you use a multiplexer, you need to have an input going into that multiplexer. But anyway, for all that control that we discussed, this is the finite state machine that you can find in the book for that one. This is incompletely specified. Not all the control signals are specified here. The control signals for the say reg source and stuff like that are not specified, especially the control signals that are related to the decode step, this guy. They are not specified here. Why? Because in the book they use a separate instruction decoding combinational block in the control for the decode step, so they don't have that specified over here. But in terms of multi-cycle data path, that basically ends the discussion for multi-cycle data path. Thank you, everyone.